Okay, so let's talk about the basics of linear regression. And so what is linear regression? So this is a method of organizing data that uses the method of ordinary least squares to determine which line best fits the data. And so here we're going to be talking about simple linear regression mainly. And so that's linear regression that describes the relationship between a dependent variable and a single independent variable. And it enables us to determine the direction and strength of that relationship. And if we were talking about multiple linear regression, then in addition to our dependent variable and independent variable, we'd have other variables that we could also control for. And so importantly, this method provides us an equation that estimates the change in our dependent variable y per 1 unit change in the independent variable x. And so this equation is really important, and being able to estimate the change in your dependent variable given a 1 unit change in your independent variable is something that's very important for prediction and for research. And so let's look at an example here. And so let's say we were interested in the relationship between hospital charges and hospital length of stay. And so our dependent variable, which is usually referred to as y, is hospital charges per admission, and our independent variable, usually referred to as x, is hospital length of stay in days. And so let's say we have 20 observations, and they're plotted in the chart below, each of them having an x and y data point so that they make up a coordinate on the two-dimensional chart. And we always put our independent variable on the x horizontal axis, so that's length of stay in days, and the dependent variable y on the vertical axis, and that's charges. And you can see that as the length of stay increases horizontally, the charges also tend to increase vertically. And so this would be called a positive relationship, which is something we discussed in our module on correlation and association. The line on this graph represents the least squares line. And so this is the line that minimizes the distance from each of those individual data points to the line on the graph. And you can see there, based on the coordinates, how if you had the coordinate of x and you just had that line, you could move up and find a predicted y coordinate. So where does the data come from? So much like in our unit on association, we want to obtain a random representative sample on the previous slide. It's of individuals from the population of interest. In your homework assignment, it's going to be on hospitals. On each individual, you want to measure both the variables of interest. You call variable x the independent variable, and you call variable y the dependent variable. And so each variable would be entered as a column of data in a Microsoft Excel spreadsheet, and each individual case or individual is a row that contains measurements for both x and y made on that single individual. And so the first thing you want to do, as we did in the unit on association, is start with a scatter plot. And so this should be created prior to calculating any regression statistics. It's very easy to create in Excel. And it visually displays the relationship between the two variables. As we saw on the previous slide, the x and y coordinates on a two-dimensional graph. And this really enables us from the get-go to determine whether we think a linear relationship actually exists. If there is no linear relationship in the data, then we're not going to be able to use linear regression. So let's look at these scatter plots that we looked at previously in Module 10. And so here you can see an example of a positive linear relationship, right? As x increases, the value of y also increases. This is a strong association. So if we were to draw a line through the data, which would be our regression line, all the data points would be very close to that line in a tight cluster around it. Similarly, we could have a negative linear relationship. So as x increases, the value of y tends to decrease. In this example, the association is a little weaker, but you can tell by looking at the data points, clearly a linear relationship exists, and you could draw a line through that data. Lastly, if you were to plot the data and get something like this, you could tell right away, there's no linear relationship here. As x increases, there's no systematic change in the value of y. And so based on this scatter plot, you wouldn't even bother with trying to do linear regression with the data at all. Okay, so let's talk about the ordinary least squares regression line. This is typically referred to as OLS. And so this is the line that fits through that cloud of data points in a scatter plot that minimizes the sum of the squared deviations of all those points from the line. And there are two basic equations that I want you to know. I'm showing on the screen there. The first is y hat equals beta naught plus beta 1x, and then y equals beta naught plus beta 1x plus e. And so now I'm going to talk to you about what these two equations mean. So the first thing you should know is that the equation that says y hat, that is the predicted value of y based on our regression line. So that's the value of y that you would find on the straight line that you saw on the previous graph. Y without the hat on it is the true value of y shown in the data points that are plotted on the graph. And both of these equations are important. And so the first thing, b with the underscore 0, which is referred to as beta naught, this is the y-intercept. And so this is a constant value, and it's the value of the dependent variable y when x equals 0. And it's literally the value of y when that line crosses over the y-axis where x equals 0. Beta 1 is the regression coefficient. And so when we do a linear regression, beta 1 is really what we're the most interested in. This is the slope of the regression line, and it represents the amount that our dependent variable y changes when our independent variable x changes by 1 unit. And if we were to use the language of calculus, this is also referred to as the derivative. And so the whole reason why we do regression is because we're interested in this value, beta 1, the regression coefficient. We want to know the impact that x has, that a 1 unit change in x has on y. Y hat, as I mentioned, is the value of y predicted by our OLS regression line. So once we've computed beta naught, the intercept, and beta 1, the regression coefficient, we have our value of x. We then use the equation number 1, to come up with a predicted value of y for each and every observation. And so this is the value of y predicted by our regression line. E is the error term, also referred to as the residual. This is how far our predicted value of y is off. So you can see in equation number 2, the true value of y is equal to our intercept plus our regression coefficient multiplied by our independent variable plus an error term. And that error term, as you can see in the equation in the bottom, is equal to the true value of y minus the predicted value of y. Or another way of putting that is it's equal to the true value of y minus beta naught plus beta 1x. Okay, so how do we calculate these terms? And this is something you're going to be doing in your assignment. And so we want to calculate, there are several things we want to calculate. We want to calculate our regression coefficient, beta 1, our y-intercept, beta naught, and then once we have that, we can calculate the predicted value of y, our dependent variable, which is y hat, and the error term referred to as e. So what do we start out with? We start out with a random sample of x and y values entered in 2 columns in an Excel spreadsheet, and the 2 OLS equations that I showed you on the previous slide. The first thing is we want to calculate the regression coefficient, beta 1. And you can see the formula there. It should look familiar to you. What you do is in the numerator, what you're doing there is you're subtracting, first you want to compute the mean of x and the mean of y. Then you subtract the mean of x from each individual x value in your data. You subtract the mean of y from each individual y value in your data. You multiply those two results together at the individual row level for each individual data point. And then you sum up that value over all the data points. And you divide that by, in the denominator, that should look very familiar to you because we've done it earlier in the course, that's the sum of squares on x, right? where you're subtracting the mean of x for each individual data point, squaring it, and summing it. And so beta 1 is equal to the numerator divided by the denominator. And so this represents the slope of the least squares regression line. And it's what that represents is it's actually the ratio of the covariation between both variables x and y to the variation of the independent variable on its own. The next thing you want to do is calculate the y-intercept. And so once you have beta 1 and the mean of y and the mean of x, this is very easy. The y-intercept, beta naught, is simply the mean of your dependent variable y minus your regression coefficient beta 1 multiplied by the mean of your independent variable x bar. And so then you got your y-intercept. Well, once you got your regression coefficient and your y-intercept, then the third step is you calculate the predicted value of y for each individual observation in the sample. And so that y hat has a little I there. That means you're doing it for each individual observation in the sample. And that's equal to the y-intercept, beta naught, plus the regression coefficient, beta 1, multiplied by whatever the value of x is for that observation. And so you get what you end up with then is a predicted value of y for each individual observation based on the regression line. Well, the next step, the fourth and last step, is you want to calculate the error term or residual for each observation's predicted value of y. And remember, you have the actual value of the dependent variable y. You have each individual observation, and all you do is you subtract your new predicted value that you calculated in 3 from the actual from the actual value of y, and that gives you the amount of error for each individual observation. And that amount of error is the distance from the plotted data point to the straight line that goes through the data. Okay, so let's look at an example. And we talked about this example of the relationship between hospital charges per admission as the dependent variable y and hospital length of stay in days as the independent variable d. So if we had 20 patient observations that I showed you previously plotted on the graphic you can see below there, each with an x and y data point, I'm showing you on the left-hand side what the data actually looks like in the spreadsheet. So you have in rows from patient 1 through patient 20, you have variable y, the dependent variable, charges per patient, and then you have next to that in the third column their length of stay in the hospital in days. That's the x variable. Well, the next thing you want to do after that is calculate y bar and x bar, which are just the mean of y and the mean of x. And so you can see in that little the little table above the graphic there where I've done that. So once you've done that, then you can subtract the mean of y from y. So that's the fourth column in the data where it says y minus y bar. And then I'm doing the same thing for x, right? I'm subtracting the mean of x bar, from each individual x observation. And so you can see in the data where I've done that. And so after I've done that, then it's easy to calculate the numerator for our beta 1 regression coefficient, which in the table there, that's the sum of y minus y bar multiplied by x minus x bar. So you can see the column in the table there, the second column from the end, y minus y bar multiplied by x minus x bar. I'm just summing that up and putting that in the little table. Then I've also done the sum of squares on x minus x bar. So you see I've squared the x minus x bar values in that last column of data, and then I just sum all those up, and that's the denominator. And so for the beta 1 regression coefficient, it's simply that numerator, the sum of y minus y bar multiplied by x minus x bar, divided by the denominator, the sum of x minus x bar squared, the sum of squares. And so there you go, we got the regression coefficient, and here it's 806. I'll talk about on the next slide what that means. And then lastly, we calculate the y-intercept using, remember the formula from the previous slide, it's equal to the mean of y minus our regression coefficient multiplied by the mean of x. And so we have that information in the little table there to calculate our y-intercept. And so now we have the formula for our regression line, y hat equals beta naught plus beta 1x. And that is equal to, our y hat here are charges, right? Hospital charges. It's equal to 1,045 plus 806 multiplied by the length of stay in days, because charges is our y variable, length of stay is our x variable. And so what our regression line predicts, we're really interested in the 806 number. It's predicting a $806 charge increase for each additional day increase in length of stay. So for every additional day a patient stays in the hospital, their charges increase by $806. That kind of makes sense, doesn't it? The y-intercept value of $1,045 there really represents the fixed charge of an admission. So that's kind of what you're starting out with, or the charge if you had a 0-day stay. And so the next step, once you have this regression line, is you would plug in the actual value of length of stay for each individual observation, and that would enable you to get the predicted charges shown on the regression line, right? For each individual x value, you're plugging that into length of stay in days, and that equation, charges equal 1,045 plus 806 times length of stay in days, will give you a predicted y value that equals that regression line shown there in the graphic. And so the other interesting thing about this graphic is the distance between the true values plotted in the diamonds on the graph and the line is the error term. And so in the table on the right-hand side, the columns, I have the predicted values of y given what we had on the previous slide for the values of x and our intercept and our regression coefficient. And then I'm showing right beside it in the table the actual value of y. And so then the error is just the error term is the predicted value of y subtracted from the actual value of y. And so you can see what the error term is in the far right-hand corner there. Okay. So there are a few assumptions for linear regression. The first assumption is that each value of x and y is normally distributed. Second assumption is that the standard deviation of the outcomes y do not change over the variable x, so the variance doesn't change. Thirdly, we're also assuming the outcomes y are independent from each other, so each patient case is not dependent on the other patient cases in this instance. Fourthly, we're assuming a linear relationship exists between x and y. All right. There's also multiple regression. I'm going to touch on this briefly. It's not going to be in your assignment. Multiple regression is just an extension of simple linear regression, in which there are more than two independent variables. So we basically, in addition to y and x, we also have additional x independent variables. And we do this in order to control for potential confounders. So if you look at the equation below there, typically the notation y is the dependent variable. And each independent variable is referred to by an x with a subscript, so x1, x2, ... all the way through xk, or whatever our last independent variable is. And then each slope coefficient or regression coefficient would be referred to by beta 1, beta 2, etc. There are some assumptions for multiple regression. There are 4 important assumptions. First is that the error terms on the multiple regression are normally distributed. Secondly, the mean of the errors is 0, so this is also going to be true for simple linear regression. Thirdly, the errors have a constant variance. And fourthly, the model errors are independent of each other.